The early hours of January 15, 2025 witnessed a significant lunar launch. Firefly Aerospace's Blue Ghost Mission 1, or BG-1, soared into the night sky on a SpaceX Falcon 9 rocket. The launch at 1:11 a.m. EST from Kennedy Space Center marked a milestone in commercial lunar exploration. BG-1 carries 10 unique payloads for the lunar surface. This mission is part of NASA's Commercial Lunar Payload Services, or CLPS initiative. Governments are partnering with private companies for ambitious space goals. BG-1 aims to land near Mont-Latreille in Mare Crisium. The Blue Ghost lander is set to touch down around March 2, 2025. This mission represents the largest CLPS delivery to date. The success of BG-1 could pave the way for more ambitious missions. Let's delve into the scientific treasures aboard this lunar-bound spacecraft. The 10 payloads aboard BG-1 represent a diverse array of scientific instruments and technological demonstrations. Each payload is meticulously designed to address specific questions about the moon's environment, composition, and potential resources. From studying the moon's internal heat flow to testing advanced navigation systems, these experiments hold the key to unlocking a deeper understanding of our celestial neighbor. One of the primary focuses of this mission is to gather data that will support NASA's Artemis program. Artemis aims to establish a sustainable human presence on the moon, and the knowledge gained from BG-1's payloads will be crucial in achieving this ambitious goal. By studying the lunar environment in detail, we can develop safer and more efficient technologies for future crewed missions. Among the payloads, some stand out for their potential to revolutionize our understanding of the moon. LISTER, for instance, will delve into the moon's thermal history, while LPV will attempt to collect samples of lunar regolith, the loose dusty material covering the moon's surface. Other payloads like NGLR and LUGRI will test cutting-edge technologies crucial for navigating and communicating on the moon. These technologies are vital for future lunar exploration, enabling precise landings and reliable communication networks. The lunar surface, exposed to the harshness of space, may seem geologically inert. However, beneath its desolate exterior lies a fascinating story of internal heat and potential volcanic activity. Unraveling this story is the task of LISTER, or Lunar Instrumentation for Subsurface Thermal Exploration with Rapidity, one of the most anticipated instruments aboard BG-1. LISTER's mission is to characterize the moon's heat flow, a measure of how much heat escapes from the lunar interior. This heat, a remnant of the moon's formation and the decay of radioactive elements within its core, plays a crucial role in shaping its internal structure and evolution. By understanding the moon's heat flow, scientists can gain insights into its thermal history and predict its future geological activity. To accomplish its mission, LISTER will employ a novel approach: pneumatic drilling. LISTER will drill several meters into the lunar regolith, deploying sensors to measure the temperature at different depths. The data collected by LISTER will be invaluable in refining our models of the moon's internal structure and composition. Lunar regolith, the fine, powdery layer blanketing the moon's surface, holds clues to the history of our solar system. This regolith, formed over billions of years by micrometeoroid impacts and solar wind bombardment, contains a record of past events and processes that have shaped the moon's surface. Extracting this valuable scientific treasure is the primary objective of LPV, or Lunar Planet Vac, another innovative payload aboard BG-1. LPV, as its name suggests, is essentially a lunar vacuum cleaner. However, instead of relying on suction, LPV utilizes a unique system of compressed gas to collect samples of lunar regolith. This method allows for the collection of pristine samples from various locations and depths, minimizing contamination and preserving the scientific integrity of the gathered material. The samples collected by LPV will be analyzed for their chemical composition, mineralogy, and age. This information will provide insights into the moon's formation, the evolution of its surface, and the bombardment history of the inner solar system. Understanding the properties of lunar regolith is crucial for future human exploration. LPV's mission represents a crucial step towards unlocking the secrets held within lunar regolith and paving the way for future human endeavors on the moon. The moon, our closest celestial neighbor, has been a constant presence in our night sky for millennia. Yet, despite its familiarity, the precise distance between Earth and the moon has been a subject of scientific inquiry for centuries. Refining our measurements of this distance is not just an academic exercise, it has important implications for understanding the dynamics of the Earth-Moon system and testing fundamental physics. Enter NGLR, or Next Generation Lunar Retroreflector, a payload aboard BG-1 tasked with demonstrating a novel method for measuring the Earth-Moon distance with unprecedented accuracy. NGLR achieves this by utilizing a technique known as lunar laser ranging. This technique involves firing laser pulses from Earth-based stations towards retroreflectors placed on the Moon's surface. The retroreflectors, essentially highly reflective mirrors, reflect the laser pulses back to their source. By precisely measuring the time it takes for the light to travel to the Moon and back, scientists can calculate the Earth-Moon distance with remarkable precision. NGLR's retroreflector, designed for enhanced performance and longevity, promises to significantly improve the accuracy of these measurements. The data collected by NGLR will not only refine our understanding of the Moon's orbit, but also provide insights into fundamental physics. The lunar surface, while visually stunning, presents a unique challenge for exploration lunar dust. This fine, abrasive dust, formed by micrometeoroid impacts, poses a significant hazard to both robotic missions and future human explorers. Lunar dust can clog mechanisms, scratch instruments, and pose health risks if inhaled. Tackling this challenge is crucial for long-term lunar exploration. Two payloads aboard BG-1, RAC and EDS, are dedicated to understanding and mitigating lunar dust challenges. RAC studies the properties of lunar dust and its interaction with materials. This information helps design dust-resistant spacecraft and equipment. EDS uses electric fields to repel dust particles. If successful, EDS could revolutionize lunar exploration by mitigating dust hazards. The launch of Firefly Aerospace's Blue Ghost Mission 1 marks a pivotal moment in the burgeoning era of commercial lunar exploration. As NASA and other space agencies worldwide increasingly partner with private companies, we can expect to see a dramatic increase in the frequency and ambition of lunar missions in the coming years. This new era of lunar exploration promises to unlock scientific discoveries, technological advancements, and economic opportunities. The success of BG-1 and other CLPS missions will pave the way for more sophisticated payloads and ambitious scientific objectives. We can anticipate missions dedicated to resource prospecting, lunar geology, and even the search for evidence of past or present life. The Moon, once considered a desolate and barren world, is now a prime target for scientific exploration and human endeavors. The private sector, with its innovative spirit and drive for efficiency, is poised to play a leading role in this lunar renaissance. Companies like Firefly Aerospace, SpaceX, and others are developing reusable spacecraft, advanced robotics, and cutting-edge technologies that will make lunar exploration more accessible and affordable than ever before. The seeds planted by missions like BG-1 are poised to blossom into a vibrant lunar economy, expanding humanity's reach into the cosmos and inspiring generations to come.